So Ksp is all about the solubility of ionic solids. And in Chem 1A, we learned that some solids are soluble and some solids are not soluble. That was because in Chem 1A, you didn't know what a K value was. You didn't know what equilibrium was. And quite frankly, you couldn't handle it at that point. So we made it simple and we said it is or it isn't soluble based on some very basic rules. Now you know enough to understand that everything is somewhat soluble, even if it's just a little bit, and that's based on these Ksp values. Large Ksp values means it is very soluble. It will dissolve in water. You'll get a lot of ions. Very small Ksp values means that it's not very soluble and it will stay in the solid form for the most part. Then we can go further and we can say, okay, if I have so many ions in my solution, moles per liter, I will have enough that it will precipitate. And that's the difference between Q and K. K is at equilibrium for that temperature. Q is at any point. Have you put more in than you need? And if that's the case, if you put more in than you need, you're going to get a precipitate. So, Ksp is less than Qsp. It will precipitate. And remember, K is calculated at equilibrium. Q can be calculated at any time, before or after equilibrium. Have you gone too far? Are you not far enough? That's it. And if Q is greater than K, you're going to see a precipitate form because that means you have more ions than what will dissolve in water. And if you have more ions than will dissolve in water, you're going to get a precipitate. All right, so in this example, 150 milliliters of 0.00394 molar barium chloride and 550 milliliters of 0.00775 molar potassium sulfate are mixed. Will a precipitate form? The Ksp for barium sulfate is 1.1 times 10 to the negative 10th. So we're talking about this reaction. The Ksp equation would be the concentration of barium ions times the concentration of sulfate ions, which equals 1.1 times 10 to the negative 10th. And the question is, for this given situation, will a precipitate form? And the way we find that out is we calculate Q. We see, is Q greater than or less than K? And in order to find Q, we need to know the barium concentration and the sulfate concentration in our solution. So to find that, I need to know moles of barium and moles of sulfate using the molarity values. 0.00395 molar is moles over 150 milliliters, but it has to be liters, so 0.15 liters. So I have 0.00593 moles of barium in my solution. Sulfate is 0.00775 0.75 over 550 milliliters, or 0.55 liters. Point 0.00426 moles of sulfate. Okay, so to put into my Q equation, I have to know the concentrations. And all I have right now are moles. So I'm going to divide moles by liters. I mixed 150 milliliters with 550 milliliters to get 700 milliliters. So divided by 0.7 liters. Gives me 0.000847 molar barium ions. Same thing here, divide by 0.7 liters. I get 0.00609 molar sulfate ions. I plug those in to find Q. 0.000847 times 0.00609 . Oh, I forgot a zero here, 0.000. And I get a Q that is 5.16 times 10 to the negative 6. Q is greater than K, which means I have more solid than I do at equilibrium, which means I will have a precipitate. And that's how you would reason through a problem like that. Q is greater than K, so it will precipitate. Questions? No? Does KSP make sense to you? We have to be careful though with KSP values for things that are not a 1-to-1 or a 2-to-2 ratio. So if it's like 1-to-2 or something like that, you need to solve for X, which is the molar solubility, which tells you the moles that dissolve per liter. Molar solubility, moles per liter, which goes back to the molarity, the X value. Good? Okay? The next thing I want to talk about is the common ion effect. Go ahead and write that down. So what this is is you're trying to dissolve a solid into a solution that already contains one of the ions. It's like trying to dissolve silver chloride in salt water. There are already chloride ions taking up that space, so less of it dissolves. And we're talking about molar solubility here. So given the Ksp for silver chloride is 1.58 times 10 to the negative 10th, calculate the molar solubility of silver chloride in pure water. So this is just silver chloride in pure water. That's what it looks like. And my K equation would look like that. And they tell me it's because it's a 1 to 1 to 1 ratio, we can say that this is x squared, right? And to find x, I take the square root which is 1.26 times 10 to the negative 5th moles per liter. That's my molar solubility of silver chloride in pure water. That's how many moles of silver chloride will dissolve in a liter of water at that temperature. If I increase the amount of water, I'll increase the number of moles. It's moles per liter. Okay, so that's for pure water. And if I did an ice table for this, you don't have to do this if you don't want. We would leave out the silver chloride because it's a solid. You don't include solids in your ice tables. We would start with 0, 0, it's pure water, plus x, and I would wind up with Ksp equals x squared. And you would solve for x. Right? Does everybody kind of see the value of ice tables at this point? Hopefully. All right, but part B says a solution that has a silver ion concentration of 5.5 times 10 to the negative 3rd molar. So this time, I'm not starting out with 0 silver. I'm starting out with some silver and no chloride. I have an initial concentration of product. I'm trying to dissolve this in a solution that already has silver in it. Does everybody agree that that's going to decrease the amount of solubility? How much it's going to dissolve? There's already junk in there. Okay. Same thing though. Plus x, plus x. Ksp equals 5.5 times 10 to the negative 3rd plus x times x. I was given Ksp. And then I can factor this. I get 5.5 times 10 to the negative third x plus x squared. And then what? How do I solve for x with this? Quadratic, right? I have an x squared, an x, and a number, so I'm going to do the quadratic equation. But you don't. You don't ever do the quadratic equation in AP Chemistry. Here's how you deal with this. And this is kind of a solution to a lot of our issues that we have in this unit. We make the assumption, or we know, that x is going to be a small number no matter what, right? And when we square small numbers, what happens to them? They get even smaller, right? Things to the negative exponent squared get even tinier. So we're going to have this biggish number plus this really small number. To the point that this really small number is insignificant. The best example that I can give you is a billionaire drops a penny on the ground. Is that significant to a billionaire? No. Adding this to this is so small of an addition, we don't even have to worry about it. So we solve for x, which is the molar solubility. And we get 2.9 times 10 to the negative 8. Did my molar solubility go down when I had other stuff in there to begin with? Yes. It went from 1.26 times 10 to the negative 5th moles per liter would dissolve to now only 2.9 times 10 to the negative 8 moles per liter will dissolve because there was already stuff in there. It reduces the solubility. Questions? Does everybody see how I can make this assumption? Okay. That's it.